Alright, salut tout le monde. Welcome back to another differential geometry reading stream, or as they could be called right now in this section of the book, which, by the way, we're reading Differential Geometry by Erwin Kreisig. This part of the book, though, might be properly called Riemannian geometry reading streams. We're currently in chapter 7, which is ostensibly on absolute differentiation and displacement. But as I've mentioned in previous episodes now, particularly starting in, say, section 74 or section 73, which included the Ricci identity and the Bianchi identities. And when I got to those, I said, hold up. These are definitely considered not really within the scope of what's called smooth manifold theory, but it's more under what would be known as Riemannian geometry. And so that kind of threw me for a loop. And I mentioned this before also with the whole, like, this book, Differential Geometry by Erwin Kreisig, one of the main criticisms is how the notion of a metric is handled. How is that different from a metric seen in other parts of math as opposed to like a Riemannian metric? And then, we're going to throw, the prefix of Riemannian onto everything. Riemannian manifold, Riemannian tensor, Riemannian curvature. But then all of the treatments in this book were limited to the dimension of 3. And then part of this is like, well, you want to learn differential geometry as a means to the end of learning about general relativity in physics. But then it's like, okay, well, space-time is 4-dimensional. So that's the second big criticism. The first one's about metrics. Second one is like, okay, we're going to just dance around the idea of a Riemannian manifold, but we're never going to actually like handle that explicitly in this book. Okay, and now we get to where we are now, chapter 7, absolute differentiation and displacement. And okay, I looked at Bianchi identities and I was like, we can, look at a, much more advanced graduate textbook level where there's, Lie derivatives going on and stuff like that. Or we could look at gravitation, Misner, Thorne, and Wheeler. That's a physics textbook. And there's a whole 15 pages all about the Bianchi identity. And it's a very different treatment than the just single page here in differential geometry. So, okay, then we get to section 75 where we are now, differential parameters of Beltrami. And that's all good, but then the next section is section 76. Keep in mind, I'm talking about right now the Dover edition here, which is going to be important for where this rant is going in just a moment here. Section 76 is on, it's called Definition of the Displacement of Levi-Civita. First of all, that whole terminology, displacement of Levi-Civita, is a little bit misleading / confusing. What we really want to be talking about is the connection of Levi-Civita. Okay, but section 76 here is one of the longest sections of just straight text going on, where it's uninterrupted by, there are no theorems or a lot of proofs or problems to really break it up, but just like a long section of a lot of text. And then we have a few more sections, 77 and 78, which are going a little bit more in detail, supposedly on the displacement of Levi-Civita, and then a general definition of absolute differentiation and displacement. But here's the thing, like I just mentioned, it's like, if you look at other sources, they don't really talk about a displacement of Levi-Civita as much as emphasizing a connection of Levi-Civita. And this is where I had this realization, okay? I brought this up in previous episodes. Erwin Kreisig, the author of this book, was more or less a postdoc in Germany right before coming to America to Stanford in like the late 50s. And at Stanford at the time were these big, it was like a big group of analysts basically, among whom a big name, a big alpha mathematician, let's say the big dog, would be Stefan Bergman, who actually Erwin Kreisig dedicated this book to, right? But before he came to America, he was basically like a postdoc doing stuff with, like, just basically n-dimensional manifolds, more or less, like differential geometry, kind of, it seems. Then he comes to Stanford. It's a little more focused on the analysis, so like the complex analysis. But anyways, in the late 50s, this book comes out, like what would become this book. Because then in 2008, Dover, or like, I don't know, early 2000s, Dover picks up that 1959 edition, because I guess that was originally published by like the University of Toronto. That's what eventually became like literally what's in this book. So think of it as like Erwin Kreisig was a postdoc doing stuff in differential geometry. He's really, his background is complex analysis. He comes to Stanford, he meets Stefan Bergman, he really gets his complex analysis juiced up. He releases, first time he releases his book, it's in Germany, in German. Comes to America. I mean, I guess Toronto is, Canada. But, okay, that's 1959. 10 years later, he comes out with a new book called Intro to Differential Geometry and Riemannian Geometry. And I actually have this book open right here. I guess that's what's here on the left, but I'll just make that the big screen right now. And I'll get all the way back to the beginning here. So here we are. Intro to Differential Geometry and Riemannian Geometry. And, I mean, we didn't see that it's by Erwin Kreisig. There we go, by Erwin Kreisig. And, again, dedicated to the alpha, apparently, Professor Stefan Bergman. So we can just look at the table of contents, and we can glean already that a lot of this is identical to what's in the differential geometry book here. Theory of curves, first fundamental form, notion of a surface. Second fundamental form, it looks pretty much identical. Tensors, okay, basically he just like pulled that out of the first fundamental form chapter, which is chapter 3 in what we have read in the differential geometry book. That's its own chapter now. Same with formulae of Weingarten and Gauss, coming out of the second fundamental form chapter. Geodesic curvature and geodesics, a few of these topics are in the last chapter of the book we're reading. So like these surfaces of constant Gaussian curvature, spherical surfaces of revolution, pseudo-spherical surfaces of revolution. That's all in the last chapter of the physical book that I'm reading. And then this is where things get interesting. It's like, obviously a lot of this is the same, and it's just, in a slightly different order, or things are put in chapters where they weren't before. But then we get to the end of right here, the absolute differentiation chapter, and the whole Levi-Civita connection stuff has been basically rewritten, it seems like. Because then, yeah, we have special surfaces, and then we also have now tacked on what I honestly expected would have made the earlier cut, but maybe was like removed because of like length limitations. We have actually going through like, Riemannian manifold, and then do some generalizations, submanifolds, do some theorems and proofs off of that. And then, here we go, even more. So, where am I going with this? Intro to Differential Geometry and Riemannian Geometry. This is like 9 years afterwards, okay? And it's basically a substantial overhaul, particularly of sections that I'm coming to now, and that's what kind of threw me for a loop. Whatever that means, you know what I'm saying. But yeah, that sort of is like why I haven't read from this book every single week lately, is because I really needed to like orient myself freshly within the landscape, if you will. And yeah, that was 10 minutes of ranting, so that might as well be a limit. But oh well, what I was going to say is that I'm going to read everything from the differential geometry book here, right? But I'm also going to read what's in Intro to Differential Geometry and Riemannian Geometry, the book that was written 9 years after. Because then, right, what I alluded to, and I already said, was Dover then went back to the 1959 University of Toronto edition. Like, you could think of what's on the screen right now. That one's like the third edition. This is like the second edition of like Kreisig notes. And then there was like, the first edition was originally in German. And then Kreisig we probably know him, or a lot of you guys might know him, for writing the advanced engineering math textbook, which like a bunch of universities use. So Kreisig got a deal with the university publishers basically to, distribute that advanced engineering math book. So like as far as we're concerned, Erwin Kreisig is like the Stephen King of advanced engineering math texts, right? And so they probably Dover, now I'm talking about, went to him in the early 2000s, and they're like, okay, we already know that you're the Stephen King of advanced engineering math. What other books do you have in your backlog that we can maybe spin off and, get a big book deal with? But he's like, okay, Intro to Differential Geometry and Riemannian Geometry is like, really the apex, the gold stuff. That's the good, he put the most work into that. So he's like, well, that's just going to be with the University of Toronto. Here's like, it's not the German version, but here's this second edition. And then that's what they reprinted. I think that's what's going on. That's why you can get this book for like, okay, whatever. It was $13 the first time I bought it 10 years ago. Now it's like $18 thanks to inflation. Maybe it's more now, for all it could be last time I checked it. But yeah, because the Intro to Differential and Riemannian Geometry copies are like $50, $60. And it's like, no one is really going to use that anymore. We're just going to buy John Lee Smooth Manifolds, John Lee Intro to Riemannian Manifolds, you know what I'm saying? Anyways. Oh, yeah, and this is the last thing, is I finally found also, because in the PDF of the Dover Differential Geometry book, in the PDF that I originally had, in a lot of these critical sections now, there are pages missing from the PDF, which is kind of like, makes me wonder, right? Because it seems like someone obtained the PDF initially, and then they removed the pages of the critical sections they wanted to like print out and distribute, put on their faculty website or whatever. And then eventually that copy with the pages removed got, tossed around the internet as well, and that's what I eventually got my hands on. But I finally found a copy that has the pages in there, so it's not as much of a pain to do this. So, getting attacked by this wild black man. Okay, here we go. Section 75. Differential parameters of Beltrami. Let phi of u1 and u2 and psi of u1 and u2 be scalar functions of class r greater than or equal to 2 of the coordinates u1 and u2 on a surface. the gradients, phi with a subscript comma alpha, which is equivalent to the partial derivative of phi with respect to u alpha, or partial phi partial u alpha, and psi with a subscript comma alpha is equivalent to the partial derivative of psi with respect to u alpha, or partial psi partial u alpha, are covariant vectors for which refer back to section 71. Hence the expression nabla of phi and psi, or del of phi and psi, is equal to g superscript alpha beta then times psi sub comma beta, which is equal to, or the same as, g superscript alpha beta then times partial phi partial u alpha partial psi partial u beta, is an invariant with respect to allowable transformations of the coordinates. Del, or nabla, is called differentiator of the first order, or first differential parameter of Beltrami. It was already used by Gauss and Lemay. Instead of del and then each of its inputs listed individually, we just write briefly, or say simply, del of those inputs. So del phi is equal to g superscript alpha beta then times phi sub comma alpha then times phi sub comma beta, which is equal to g superscript alpha beta then times partial phi partial u alpha partial phi partial u beta. This expression is the square of the length of the gradient of whatever its inputs are. Oh, and I guess this is an OCR document, so those null symbols should be phis. So this expression is the square of the length of the gradient of phi, as can be seen from 35.3 back in section 35, which is just the statement that the magnitude of the vector A is equal to the square root of the scalar product of A with itself, which is equal to the square root of g sub alpha beta then times A superscript alpha then times A superscript beta, which is the same as the square root of A sub alpha then times A superscript alpha, which is also the same as the square root of g superscript alpha beta then times A sub alpha then times A sub beta. In the case of Cartesian coordinates in the plane, we have that these components of this metric, or some would call it the first fundamental form g, we have g superscript 1 equals g superscript 2 equals g, which equals g superscript 1 which equals 1, and then we also have that g superscript 1 is equal to 0. Therefore, we may write that del of phi is equal to the square of partial phi partial u1 plus then the square of partial phi partial u2. And again, we have a little OCR typo going on here and throughout the next couple of paragraphs, but if phi in terms of u1 and u2 is a function of u1 and u2, not a constant, and if du alpha dt are the components of a contravariant vector tangent to a curve of the family phi of u1 and u2, which is equal to a constant, then partial phi partial u alpha du alpha dt is equal to 0. That is, at any point of the curves, namely phi in terms of u1 and u2 equal to a constant, then the gradient partial phi partial u alpha is orthogonal to the corresponding curve. Let us now consider two families of curves, phi in terms of u1 and u2 equal to a constant, and psi in terms of u1 and u2 equal to a constant, which form a net. Since the gradients are orthogonal to the corresponding curves, they make the same angle gamma as the curves, and we have a form which is reminiscent of forms we have seen before so far in reading this book. That is, cosine of gamma is equal to a fraction in the numerator. We have del of phi and psi all over the square root of del phi del psi. We thus obtain the following, theorem 75.1. If two families of curves, phi in terms of u1 and u2 equal to a constant, and psi in terms of u1 and u2 equal to a constant, form a net, this net is orthogonal if and only if at every form del of phi and psi is equal to 0. We will now mention the following connection between the differential parameters of Beltrami and geodesic coordinates, for which refer back to section 52. We consider a family of curves, phi in terms of u1 and u2 equal to a constant, which at every point satisfy del phi is equal to 1, and which, together with another family of curves, psi of u1 and u2 equal to a constant, form an orthogonal net. And just another comment, That's that sentence at the beginning when it says we will now mention the following connection with the, you could say, British spelling of connection with an X, as opposed to connection, CONNECTION, connection. That's the only time that the word or notion connection is brought up in the section, which is a bit misleading because it doesn't mean connection as is referred to in, say, the later 1959 Intro to Differential Geometry and Riemannian Geometry, or just modern Riemannian Geometry texts, materials, websites, anything. All refers and emphasizes the connection, and so I think that's a poor choice of words there. Anyways, continuing on. Then, by the preceding theorem, del of phi and psi is equal to 0. We now introduce new coordinates, and I'm going to just pop back into the book here to make sure that I'm reading these correctly. Yeah, u1 tilde and u2 tilde, defined by u1 tilde being equal to phi of u1 and u2, and u2 tilde being psi of u1 and u2, whose coordinate curves are the curves phi in terms of u1 and u2 equal to a constant, and psi in terms of u1 and u2 equal to a constant. In these new coordinates, del of u1 tilde is equal to g tilde superscript 1, 1, which is equal to del of phi, which is equal to 1, and therefore also g tilde sub 1, 1 is equal to the reciprocal of g tilde superscript 1, 1, or that is 1 over g tilde superscript 1, 1, which is thus equal to 1. Hence, the corresponding first fundamental form is given by the expression ds squared equals the square of du tilde 1 plus g tilde sub 2, 2, then times the square of du tilde 2. That is, the u tilde 1 and u tilde 2 coordinate system is geodesic, and we can refer back to section 51 for that. By contraction, the covariant derivative a superscript alpha and then a subscript of comma beta of a contravariant vector a superscript alpha, we obtain the scalar a superscript alpha, all with a subscript, then comma alpha, which is called the divergence of the vector a superscript alpha. Namely, divergence of a superscript alpha is denoted equal to a superscript alpha and then a subscript comma alpha. This is a little bit awkward on screen, but we have using 70.3 prime, which is obviously from the previous section 70, but it reads a superscript beta and then a subscript comma sigma is equal to partial a superscript beta partial u sigma plus a superscript kappa then times Christoffel sub kappa sigma superscript beta. So using this, except rewritten with different indices, so we have a superscript alpha and then sub comma alpha is equal to partial a superscript alpha partial u alpha plus a superscript nu then times Christoffel sub nu alpha superscript alpha. And also from 47.6 prime, which is Christoffel sub alpha gamma superscript alpha is equal to 1 over 2g and then times partial g partial u gamma, which is also equal to partial in terms of u gamma of the logarithm of the square root of g, where g is of course the discriminant of the first fundamental form. So particularly going back to section 75 here, we're going to rewrite what we want with different indices, namely Christoffel sub nu alpha superscript alpha is equal to partial in terms of u nu of the log of the square root of g, which is then equal to now 1 over the square root of g, then times partial with respect to u nu of the square root of g. We thus find, using those two things from 70.3 prime and 47.6 prime rewritten in forms that are useful to us here, we find that a superscript alpha sub comma alpha is equal to 1 over the square root of g, then times partial with respect to u nu of the square root of g, then times a superscript nu, which this is then equal to 1 over the square root of g, then times partial with respect to u nu of now the square root of g, then times g superscript mu nu, then times a sub mu. If, in particular, a sub mu is the gradient of a scalar phi, that is, a sub mu is equal to partial phi partial u mu, we obtain the invariant capital delta phi, which is equal to the divergence of the gradient of phi, which is now equal to 1 over the square root of g, then times partial with respect to u nu of square root of g, then times g superscript mu nu, then times partial phi partial u mu. Now this capital delta is called differentiator of the second order or second differential parameter of Beltrami. In the case of Cartesian coordinates in the plane, we have g superscript 1, 1 equals g superscript 2, 2, which equals g, which equals 1, and g superscript 1, 2 equals 0, and therefore div grad of phi is equal to partial square phi and then partial u1 squared plus partial square phi partial u2 squared. That is, this is equal to or amounts to the Laplacian in its simplest form. So we may write the capital delta phi also as follows, or this div grad or this Laplacian as follows. In consequence of div of a superscript alpha being a superscript alpha, then sub comma alpha, we obviously have that the Laplacian of phi is equal to this large outer quantity of g superscript mu nu, then times partial phi partial u mu, closed quantity subscript comma nu. Therefore, by relation for this notation where we have the subscript comma and then a Greek character, this is from section 71, expression 71.4 is phi sub comma sigma is equal to partial phi partial u sigma. So by this, and theorem 72.1, which is from our good friend Gregorio Ricci Curbastro, the covariant derivatives of the tensors g sub alpha beta, g superscript alpha beta, and Kronecker delta sub alpha superscript beta are zero tensors. See section 72 for the proof. Because of these, we now have that the divergence of the gradient or Laplacian of phi is equal to g superscript mu nu, then times phi sub mu nu. That was a mouthful, and I ranted for like 10 minutes at the beginning. So I also planned out where the next few videos are going to go, and I honestly have like a list of like another half a dozen, 10 videos that I could also film besides these reading streams here, because I do recognize that I've been slacking so far this year. And I need to pump out some more videos for you guys. So I'm going to end this here. I'm going to edit this and I'm going to upload it and hopefully have some more videos for you guys soon. Thanks for watching. Peace.